Okay, now we are on subtopic 35.3, image formed by refractions. So in this section, we are going to describe how image are formed when light rays follow the wave under refraction model at the boundary here. Okay, between two material. Okay, consider two transparent media having indices of refraction of N1 and N2, right, where the boundary between the two media is a spherical surface of radius R, right, as in this figure, right. The object at point O, this is position of the object, is in the medium for which the refractive index is N1, right. Let's consider the paraxial rays leaving O, okay, as shown here, and then is refracted, okay, and finally combined at one point where the image going to be formed. Based on Snell's law, if you still remember, N1 sine theta 1 must equivalent to N2 sine theta 2. Okay, based on Snell's law, we are going to assume or use assumption of the theta is very small, right? Therefore, sine theta very small. Therefore, sine theta will be more or less to theta only, right? So this equation going to be simplified to N1 theta 1 equivalent to N2 theta 2. Okay, so from here, right, we are going to even make it bigger based on this diagram. Okay, so let's say consider this is the ray that we're going to consider. Okay, hitting point P here and be refracted into second medium, right, where it has index of refraction of N2, which is bigger than N1. Alright, at this point the refracted angle is theta 2. Okay, so this is the alpha angle, and here is D, and this is the center of the curvature, and we have here theta 1 is equivalent to theta 1 is equivalent to alpha plus beta, right, and beta is equivalent to theta 2 plus gamma. Okay, so how is this happen? You have to play around, because when you, let's say you have here is okay, is equivalent to theta prime. Okay, so theta prime plus theta 2 plus gamma must equivalent to 180 degrees, isn't it? And we know that beta is equivalent to 180 degree minus theta prime, and theta prime itself is equivalent to theta prime itself plus theta 2 plus gamma must equivalent to 180. Theta 2 plus gamma is equivalent to 180 minus theta prime, which is this one is similar to this. That is how we can conclude that beta is equivalent to theta 2 plus gamma. Okay, so from there, okay, we know that theta 1, okay, plus alpha plus beta, okay, and beta itself is theta 2 plus gamma, right? And make use of the assumption that the theta is very small, so sine theta will be equivalent to theta only. So now we have, and what is theta 1? alpha plus beta. Okay, plus, okay, N2 theta 2. Theta 2 is beta minus gamma. So combining these two information, you will have this one, N2 minus N1 times beta. And make use of information of tangent alpha. Tangent alpha, if the angle is very small, tangent alpha more or less to alpha, which is equivalent to d over p, which is d over p, okay, this triangle, tangent alpha, right? And tangent beta, okay, more or less to beta, which is equivalent to d over r, right? More or less, okay? And then tangent gamma is equivalent to gamma, provided that angle is very small, is equivalent to d over q, okay, this triangle, right? So combining all this information, we will have N1 over P plus N2 over Q equivalent to N2 minus N1 over R. Okay, and lateral magnification is equivalent to negative N1Q over N2P. Right, so slightly different compared to the mirror. The formula for the lateral magnification in mirror, it does not has the N, the index of refraction. It doesn't consider. Okay, for lens, yes, we need to consider the N, the index of refractions. Okay, sign convention for refracting surfaces. Okay, object location P will be positive when it is in front of the surface. We call it real object. It will be negative. Negative, it means that the object is in the back of the surface. So virtual object. For image location Q, it is positive. It means that image is at the back of the surface, real image. If it is negative, it means that the image is in front of the surface, virtual image. Alright, image height H prime. When it is positive, it means that it's upright. When it is negative, it means that the image is inverted, upside down. And the radius, if it is positive, it means that center of the curvature is in back of the surface. When it is negative, it means that the R, the center of the curvature, is in front, the C, okay, is in front of the surface. And please memorize this equation. Right, concept to example 35.5. Let's go scuba diving. Objects viewed under water with the naked eye appear blurred and out of focus. A scuba diver using a mask, however, has a clear view of underwater objects. Explain how that works using the information that the indices of refraction of the cornea, water and air are 1.376, 1.33, 1.0029 respectively. So if you refer to this value, 1.376 and 1.33, the indices of refraction for the cornea and water, actually more or less the same, almost the same, right? But very far different compared to air, because air is 1.0029. Alright, so why is this happening here? Okay, blurred and out of focus here, because the cornea and water, okay, have almost identical indices of refractions. Very little refraction occurs when a person underwater views objects with the naked eye. In this case, the light ray from an object focus behind the retina, resulting in a blurred image. When a mask is used, let's say like this, Okay, however, the air space, okay, between the object outside under the water, and then the space full or filled with air, and then our cornea, provides the normal amount of refraction at the eye-air interface, right? Consequently, the light from the object focuses on the retina, and the diver going to see the object clear, okay, compared to the naked eye just now, right? Now, concept to example 35.6. Okay, gaze into the crystal ball. A set of coins is embedded in a spherical plastic paperweight having a radius of 3 cm. The index of refraction of the plastic is N1 equivalent to 1.5. One coin is located 2 cm from the edge of the sphere. Find the position of the image of the coin. So, this is the equation, okay, for refraction, okay, within a material. And 1 over Q is equivalent to, okay, N2 is 1, okay, and N1 is 1.5, right? So, N1 is bigger than N2, remember, right? So, we will have, okay, 1 minus 1.5 over negative 3, the R, right, minus 1.5 over 2, you will get your Q is equivalent to negative 1.7. The negative sign here, okay, means that the image is in front of the surface. In other words, okay, it is within the same medium as the object. Okay, so this is your object, and here is your image. So from this diagram, you see that the coin appears, or the image appears to be closer to the paperweight surface than it actually is. Seems like closer because it's only 1.7 compared to the original one is 2 cm. Image formed by thin lenses. Lenses are commonly used to form image by refraction in optical instruments such as camera, telescope and microscope. Okay, so figure 35.22 here, where we have a part A and B here, okay, shows us, okay, the ray diagram on how, alright, real and virtual image. This is the real image, okay, and this one is virtual image, is formed by the first surface, this surface, right? And by assuming that N1 is equivalent to 1 from air, surrounded by air, okay, the lens is surrounded by air, okay, we find that the I1, image 1, formed by surface 1 satisfy this equation, okay, where Q1 is the position of the image formed by the surface 1, right? If the image formed by surface 1 is real, as in this figure, okay, then Q1 is positive, right? It is negative if the image is virtual, as in this figure, right? Now let's play equation 35.9 to surface 2. Consider surface 2, okay, at the back here, right? Okay, remember that N1 is equivalent to N, and N2 is equivalent to 1. We make this switch in index because the light ray approaching surface 2 coming from, okay, the material of the lenses towards the boundary of the between lens and the air. Okay, taking P2 as the object distance for the surface 2. Okay, P2 is object distance for surface 2. And Q2 as the image distance for surface 2 produced by the surface 2. It gives us this equation, right? We now introduce mathematically that the image formed by the first surface acts as the object for the second surface. If the image from surface 1 is real, as in figure A here, okay, we see that the physical distance P2 is Q minus T. Okay, P2 is Q minus T. But I want serve as virtual object. Okay, because it's at the back of the lens. Okay, as image, firstly it is real image. But to become as object, it is virtual object. Okay, for the second surface. Alright, because it is to the right of the surface. Okay, to express P2 as an object distant for optical purposes, it must be negative according table 35.2. Therefore, for the optical purpose, okay, we see that P2 is equivalent to negative of Q1 minus T. Not only Q1 minus T, but it must be negative Q1 minus plus T. It must have P2 equivalent to negative Q1 plus T. If the image from surface 1 is virtual, as in figure 35.22b, we see that P2 is equivalent to Q1 negative of Q1 plus T, where we have used negative of Q1 because Q1 is virtual object. Therefore, regardless of type of image from surface 1, okay, whether it's virtual or real, the same equation describes the location object of the object for surface 2 based on our sign convention just now. For a thin lens, only one whose thickness is small compared with the radii of the curvature, we can neglect the T. Alright? In this approximation, P2 equivalent to negative of Q1 directly for either type of image from surface 1. Hence, we will have equation of negative n over Q1 plus 1 over Q2 equivalent to 1 over 1 minus n over R2, which is this one. Adding equation 35.12 and 35.14 give us, adding these two equation, producing this to us, right? And finally, is equivalent to this, right? This expression relates the image distance Q of the image formed by a thin lens to the object distance P and to the lens property, which is index of refraction and the radii of the curvature. It is valid only for paraxial ray and only when the lens thickness is much less than R1 and R2, right? So the focal length F, okay, for a thin lens is the image distance that corresponds to an infinite object distance, just as with mirror. Means that at P is approaching infinity and Q will approach the F. Okay, we see that the inverse of the focal length of this thin lens is, okay, this one, okay, 1 over F is equivalent to n minus 1, 1 over r1 minus 1 over r2. This relationship, we call it Lens-Macker equation. This one is Lens-Macker equation because it can be used to determine the R1 and R2 needed for a given index of refraction and a desired focal length. Okay, conversely, if the index of refraction and the radii of the curvature of a lens are given, this equation can be used to find the focal length. If the lens is immersed in something other than M, this same equation can be used with N, okay, interpreted as the ratio of the index of refraction of the lens material to that the surrounding fluid. Okay, by using equation 35.17, okay, right, we can write equation 35.16 in a form identical to equation 35.6 for mirrors, where we have here 1 over f equivalent to 1 over p plus 1 over q. This is known as thin lens equation, okay, where it can relate the image distance and the object distance for a thin lens and the focal length of the lens. So sign convention for thin lens, okay, this is supposed to be the front side, or we call it virtual side. This is supposed to be back or real side, okay, because it based on concept of refractions. Okay, so incident light moving from front, okay, passing through the thin lens and then being refracted and then emerging to the back side and being focused at one point to form image. Okay, therefore, based on this convention, object location, the P will be positive when object is in front of the lens. It will be negative if it is at the back. We also know this as virtual object. Image location, the Q will be positive when it's supposed to be at the back. Okay, real image. If it is negative, it means that it's virtual and in front of the lens. Image height, H prime, R1 and R2, it is positive, it means that image is upright. If the R is positive, center of curvature is in back of the lens. If the H prime is negative, it means that image is inverted. And if R1 and R2 negative, it means that the center of curvature is in front of the lens. Okay, and focal length, positive, it means that converging lens. If it is negative, then it means that a diverging lens. Okay, so talking about converging and diverging lens, this is the shape of the lens. Okay, for part A or figure A here, this is actually converging lens. This one is converging lens, and this one is diverging lens. Right, so normally, okay, for diverging lens have negative focal length and thickest at the edge. Right, for converging lens have a positive focal length. Right, the F is positive and here the F is negative. Right, and thickest at the middle. Right, magnification of image, similar to mirror. For lenses, the lateral magnification is M equivalent to H prime over H equivalent to negative Q over P. Concept 2 example 35.8. Image formed by a converging lens. A converging lens has a focal length of 10 cm. A, an object is placed 30 cm from the lens. Construct a ray diagram, find the image distance and describe the image. Okay, for your syllabus, no need to construct a ray diagram actually. You must be able to determine in terms of calculation only. So Q equivalent to FP over P minus F. So substitute the rest of the information given here. You will have your Q positive 15. What does that mean by positive? Is real image, okay, which is at the back of the lens. And the M is negative Q over P. You will have negative 0.5. In terms of magnitude, it's less than 1. It means that your image is reduced by half of the size of the object. And it's negative, what does that mean? It's inverted. P. An object is placed 5 cm from the lens. Construct a ray diagram. Again, no need, okay? Find the image distance and describe the image. Right, again, calculate the Q. You will get negative 10. What does that mean by negative? Is virtual image. Where is the location? It is in front of the lens. This is the object. This is the image. Right, calculate the M. You will get positive 2. What does that mean by 2? Double the size. The image is double the size of the object. Okay. What does that mean by positive? It's upright. Okay. Left-right reversal. Right. So what if the object move right up to the lens surface so that the P is approaching 0? Where is the image? Okay, again, we are going to use 1 over F equivalent to 1 over P plus 1 over Q. From here, determine your 1 over Q, and finally you get your Q is equivalent to negative P, which is equivalent to 0. Therefore, Q is on the front of the lens, right? The Q is in the front of the lens, okay? Because it has the opposite signs to the P, right? And right at the lens surface, like visualized here. Conceptual example 35.9. Image formed by a diverging lens. A diverging lens has a focal length of 10 cm. An object is placed 15 cm from the lens. Construct a ray diagram. Find the image distance and describe the image. So for the part of construct a ray diagram, no need to do, as I mentioned before. So now find the image distance. So Q according to this equation, okay, and substitute 10 cm, 15 cm into this equation. However, for the F, we have to put negative sign because it's a diverging lens. Therefore, this one actually minus negative 10 cm. Then you will get this answer. Negative 6 cm. What does that mean? Negative means that our image is in front of our lens, right? So that is the meaning of negative here. It means that our image is virtual image. So to check or to describe the image distance, we have to calculate the lateral magnification, M equivalent to negative Q over P. So from this, you will get positive 0.4. What does that mean by this? Positive, it means that it's upright or left-right reversal. The amount or magnitude of the M is less than 1. It means that the image is reduced in size. Okay, part B. An object is placed 5 cm from the lens. This is 5 cm. Construct a ray diagram, no need for you. Find the image distance and describe the image again. So again, substituting the information into this formula, you will get negative 3.33 cm. What does that mean by negative? Again, your image is in front of your lens, okay, or virtual image. Then to describe the image, lateral magnification of it, you will get positive 0.667. It means that, okay, you have image smaller in size compared to object, and then it is upright, okay, image. Farsightedness, or also known as hyperopia. Okay, this happens when a far-sighted eye looks at an object located between the near point, this one, and the eye, this one. The image point is behind the retina. Okay, the ray focus behind the retina of the eye, resulting in blurred vision. Okay, so what should we do? We put converging lens. Okay, converging lens causes the image to be focused on the retina here. Okay, to correct the vision. Okay, so this is for those who have problem with far-sightedness. Right. Nearsightedness, myopia, right, happen when a nearsighted eye looks at an object located beyond the eye's far point. The image point is in front of the retina, again resulting in blurred vision. So what should we do? We are going to use a diverging lens, causes the image to focus on the retina to correct the vision again. So this is how we treat nearsightedness. That's all for this topic. Thank you very much for watching. Do not hesitate to ask me any question regarding this topic. That's all. Assalamualaikum.